In this video, I will explain about half an output offset voltage is due to input bias current. Output in this video, I will explain about half an output offset voltage. Output offset voltage due to input bias. Due to input bias current. Generally, input bias current. Input bias current. An input bias current IB is defined as the average of the two input bias currents. This one is half amp, inverting terminal, and inverting terminal. This one is connected to ground. IP1. Both inverting terminal and non-inverting terminal both are connected to ground. The currents are base currents are IP1 and IP2. This is VO output offset voltage due to input bias current IP. This one is plus VCC. This one is minus VCC. VO IP, not VO into IP. VO IP. That means output offset voltage due to input bias current. Input bias current IP. The input bias current IP is defined as the average of the two input bias currents IP1 and IP2. Therefore, average IP is equal to IP1 plus IP2 by 2. Where IP1 is the DC bias current flow into the non-inverting terminal. IP2 is the DC bias current flowing into the IP1 is the DC bias current flowing into the inverting terminal. IP2 is the DC bias current flowing into the non-inverting terminal. This is the average of these two currents, IP1 and IP2. Suppose both the input terminals are grounded. Inverting and non-inverting terminals are grounded so that no input voltage is applied to that op amp, but the plus minus supply voltages. Plus minus supply voltages means here the plus VCC and minus VEE are necessary to bias op amp properly. Even input voltages applied to both the inverting terminal and non-inverting terminals are grounded. Plus and minus supply voltages are necessary to bias the op amp properly. Next one is even though both of the input terminals are identical. That means both of the input transistors, not terminals. Input transistors are identical. It is not possible to IP1 and IP2 are exactly equal to each other. Both the transistors which are used at the input stage of the differential amplifier which are identical to each other, it is not possible to IP1 and IP2 are exactly equal to with each other due to internal imbalance between the two inputs. Due to internal imbalance, we use the specified input bias currents as being equal to either one of the two input currents. That means IB is the input bias current. We use the specified input bias current as being equal to either one of the two inputs current. Either one of the two inputs currents means IP1 or input bias specified input bias current as being equal to either one of the two input currents. Two input currents are IP1 and IP2. Therefore, IB is equal IP1 is equal to IP2. Generally, input bias current IB is 500 nanoamperes. Maximum at supply voltage. Maximum at supply voltages is equal to plus or minus 15 volts DC for a 741. Generally, input bias current IB is very small. Even though it is very small, the input bias current IB can carry a significant output offset voltage in circuit. This is the circuit diagram. Consider inverting terminal of the op-amp. Inverting op-amp amplifier. Circuit diagram. This one is the circuit diagram of op-amp. This one is minus sign, plus sign, Ri input resistance. This one is the R0 output resistance. This one is gain, open loop gain, dependent voltage source, AOL into VIO input offset voltage, ground. This is the load resistance RL, output offset voltage due to input bias current IB. This one is V2. This one is V1. Inverting op-amp amplifier configuration means non-inverting terminal of that op-amp is connected to ground. That means plus is connected to ground. The voltage at the non-inverting terminal of op-amp is V1. V2 is the inverting terminal op-amp voltage V2 here. This one is R1. This one is connected to ground. Generally, apply some VI voltage, apply some VI input voltage to this inverting terminal of an op-amp through R1. One more resistance is also there, that is the feedback resistance RF. This one is current is the current flow through this R1 is I1. Generally, this one is another terminal of that R1 is connected to ground. Therefore, the current I1 is 0. This one is IB2. This one is IB2. This one is IB1. The current coming from this one is Generally, VI voltage is applied to inverting terminal of an op-amp through R1. Our analysis of both the input terminals of an op-amp is connected to ground. That is the reason already V1 is connected to ground in the inverting op-amp amplifier configuration. That means non-inverting terminal of an op-amp is connected to ground. Here, inverting terminal of an op-amp is also connected to ground through R1. This is the voltage VIO, input offset voltage, that is also called as a differential voltage, is equal to 0 volts. Is equal to assume VIO input offset voltage is 0. The output offset voltage is due to input bias current only, IB1. Analysis. Here VIO equal to 0. AOEL into 0 is equal to 0. The output resistance of an op-amp is 0 ideally. Therefore, left side, right side end of that RF is connected to ground due to these three, due to these characteristics. VIO input offset voltage is equal to 0. AOL into 0 is equal to 0. Therefore, this is short circuited. RO is also 0. This is short circuited. Therefore, finally, right side end of that RF is connected to ground due to these conditions. Here V2 is there. Here R1 is connected to ground. Therefore, finally, this one is V2 terminal. This one is R1. R1 is connected to ground. This one is RF is also connected to ground. IB2 current flow through this one. IB2 current. Therefore, R1 and RF is connected to parallel. The current flow through this parallel combination is IB2. Finally, V2. This is the node R1 and RF. The current flow through this parallel combination is IB2. The current flow through this parallel combination is IB2. IB2 is the current flow through this parallel combination R1 parallel to RF. Therefore, V2, the voltage at the V2 means inverting terminal is V2 is equal to IB2 into R1 parallel to R. Therefore, V2 is equal to IB2 into R1 RF by R1 plus R. R1 plus R. This is V2. Next one is, we know that I1 plus according apply KCL to this node. I2 is the current entering into the node, and I1 is also current entering into the node. IB2 is the current away from the node. Therefore, apply KCL at this node A. This one is A. Therefore, apply KCL at node A. It means I1 plus I2 is equal to IB2. I1 plus I2 is equal to IB2. V at that node A, the voltage is V2. Therefore, I1 is equal to 0 minus V2 by R. I1 is equal to 0 minus V2 by R1. I1 is equal to 0 minus V2 by R1. And I2 is equal to, this is the I2, V0 IP. Some offset for even transistors are identical to with each other. It is not possible both IP1 and IP2 currents are equal due to internal imbalance. Now we will prove that this VOIB is due to IB2. Okay. Therefore, I2 is equal to V0 IB minus V2 by R. Second one is V0 IB into V0 IP, not into, minus V2 by RF is equal to, next one is IB2. IB2, the resistance at minus, the resistance between inverting terminal and non-inverting terminal is Ri. Therefore, IB2 is equal to V2 by R. IB2 is equal to V2 by Ri. IB2 is equal to V2 by R. Therefore, VOIB is the output offset voltage. Output offset voltage due to input bias current. Due to input bias current IP2. RA is the input resistance. Input resistance of the input resistance of the. Therefore, VOIB by RM. VOIB means output offset voltage due to input bias current, not multiplication term, is equal to V2 by Ri, V2 by RF from this expression. These terms are bring to this right hand side, V2 by. Therefore, V2 into 1 by Ri plus 1 by Rf plus 1 by. We know that Ri is ideal characteristics of an op-amp. Ri is infinity. Therefore, Ri is infinity means 1 by Ri is equal to 0. VOIB by Rf is equal to V2 into 1 plus V2 into 1 by Rf plus 1 by V2 into R1 plus Rf by R1 Rf. VOIB by Rf is cancelled. We know that V2 is equal to IB2 into R1 Rf by R1 plus R. V2 is equal to IB2 into R1 Rf by R1 plus Rf. V2 is replaced here. And the remaining term is R1 plus Rf by R. R1 is cancelled. R1 plus Rf, R1 plus Rf is cancelled. Therefore, output offset voltage due to base current IB is biasing current. IB is IB2 into R. We know that IB is equal to IB1 is equal to IB2. Therefore, VOIB is equal to IB. Output offset voltage due to input bias current is depends on feedback resistor RF. If feedback resistance is a very high value, therefore output offset voltage IB is also very high. See this one. Suppose IB is 500 nanoamperes. RF is 1 mega ohm. Therefore, output offset voltage VOIB is 500 into 10 power minus 9. RF is 1 mega ohm. 1 mega ohm means 1 into 10 power 6. 5 into 10 power minus 9 into 10 power 8. 0.5 volts. high value 0.5 volts. This is the output offset voltage due to input bias IP. Now coming to how to eliminate this offset voltage by using some compensation method that is called as R compensation used here. Another circuit here. This one is R1. This one is RF. Plus VCC minus VEE. This one is connected to ground RF. Here some compensation resistance is connected in series with the non-inverting terminal of the top. That compensation resistance is represented by ROM connected in series with the non-inverting terminal of an amp. The current flow through this resistance is IP1. Here is IP2, P2. Okay. In previous case, without this resistance, IP1 is the current flow through this non-inverting terminal of an amp. That must be equal to 0 because the V1 is connected to ground. In this case, this is the compensation circuit. IP1 is the current flow through this ROM. ROM is resistance. That means R1 parallel to that value is R1 parallel to RF. That is equal to R1 RF by R1 plus RF. We will consider this parallel combination as ROM. Biasing compensation. ROM is the compensation resistance that is connected in series with the non-inverting terminal of an op-amp. From this one, V1 is equal to IP1 into R1. V1 is equal to IP1 into R1. We know that in the previous circuit, V2 is equal to R1 parallel with RF into IP2. V1 must be equal to V2. V1 must be equal to 0. V2 means V0 is equal to VD into gain of the amp. VD is nothing but V1 minus V2 into AOL. V1 is equal to V2, that is equal to 0 into AOL. Therefore, 0. Being bracket that offset voltage is 0. Therefore, V1 is equal to V2. That will be IP1 ROM R1 parallel to RF. That is IP2. Suppose IP1 is equal to IP2, matched conditions. Therefore, ROM is equal to R1 parallel with RF. R1 RF by R1 plus R. The compensation resistor value is R1 parallel to RF. R1 parallel to RF. By using this compensation resistance ROM, bring back that output offset voltage to 0 volts. 0 volts. The conditions apply is here applied is IB1 is equal to IB2. Therefore, here the proper value of an ROM resistor connected in non-inverting terminal in parallel combination of resistance RF and R1 and RF. The proper value the proper value of an ROM resistor connected in the non-inverting terminal of an op-amp. That is a parallel combination of R1 in parallel with R. However, ROM, the use of ROM may not completely eliminate the output offset voltage. Generally, by using this one, bring back that V1 is equal to V2. The voltage at inverting terminal is equal to the voltage at non-inverting terminal, and also IP1 is equal to IP2. ROM is equal to parallel combination of R1 parallel with RF. Bring back the output offset voltage due to IB is 0 volts. Even, however, the ROM may not completely eliminate the output offset voltage VOIP. Because of that, currents IP1 and IP2 are not exactly equal.